discussing about the topic entitled Insights and Application, Investigating the Magnetic Field of Earth-Directed Coronal Mass Ejections. So I would like to thank and acknowledge my PhD advisors, Professor Spiros Patsarakos, Professor Manolis Yurgolis, and Professor Alexander Nindos. And I would like to give the source credits of the space weather hazards, figures and facts, which are referenced from Space Weather Science and Observation Gap Analysis Report for NASA compiled in 2021 by APL. So let's begin. So I would like to begin my seminar the way one of the greatest visionary of our time, Bill Gates, began his TED Talk in 8 years ago. So he began like this. When he was a kid, the greatest disaster that he was expecting to happen that will affect millions of people would have looked like this. And now he was proposing the next global catastrophe will not be looking like this, but instead it will look like this. And he given that talk 8 years ago, and the rest is history. He invested millions of dollars in it, and we passed this global catastrophe as well. So what I would like to tell us now, what the next outbreak or next global catastrophe will not be looking like either of these two, but it can look like this. So what is this exactly? What is this thing? This is trying to engulf Earth. So this, I would like to describe this figure with the help of a term called space weather. So space weather refers to the conditions in the solar system which are produced by solar activity. So the extreme activities of the sun, which are highly energetic, with highly energetic, with high magnetic field and plasma transfers, it can make extreme effects such as radio communication disruptions and endanger the life of astronauts. So I would like to describe this phenomena a bit more with the help of this video. So before diving into that, I would like to describe what does coronal mass ejections and why should we care. So the term coronal mass ejection describes the large expulsions of magnetic field and plasma into the interplanetary medium from the solar outer atmosphere, which is known as corona. So what really happens and why should we care? So let's see this. So from the solar surface, this magnetic field is ejected from the sun, and when it travels through the Earth atmosphere from the interplanetary medium, and it interacts with Earth magnetosphere, these high energy magnetic field also carried by charged particles, and when these interact with this Earth magnetosphere, this can cause this charged particle interact with this get funneled to the solar to the Earth polar regions, which is the reason of our spectacular auroral display. So CMEs and the associated SCPs are not just are not only causing auroras, which is of course beautiful to see, but it can also affect Earth magnetosphere. It can, when it is interacted with the power grid lines and things like that, it can affect the Earth communication system. So maybe we can look into that now. So into more detail. So this is a figure representations that I adopted from the NASA gap analysis report, which is compiled in 2021 by APL. So when sun erupts, this high energy magnetic field and plasma into the interplanetary space, since it often carries a high energy magnetic field and energetic particles as well, it can interact with the satellite communication, and it can directly interact with the many satellite communication, the aviation which are flying in the polar regions, and it can also cause radiation hazards to astronauts' life and the crew members in the space station such as ISS. So when these satellites get interrupted, or it get the high radiation doses and geomagnetically induced currents, it can in turn affect or induced effects in the underwater common cable lines, which is responsible for the internet we are having now, and the GPS systems. It can cause interruptions in the railway lines due to the geomagnetically induced currents. And due to these interactions with the magnetic atmosphere, it can also cause a thermospheric expansion, which will be responsible for the satellite drag in the interplanetary space. So this is an overall look of the how space weather effects can adversely affect our life in Earth. So this in turn represents how important the study of coronal mass ejections, the associated phenomena, and space weather in general. So let's look into the economic aspects if these kinds of events are happening. So this figure represents the likelihood of this events happening and the consequence of societal impact and cost. These colors represents the intensity. So in low intensity events, we get to know get to see auroras, which is good for tourism and things like that. But in case of major events, it can cause, as I mentioned, it can disrupt our power grid lines, our internet, railway, things like that. So in industrial scale, it can cause a loss of up to $100 million. And in the greatest effects, such as the atmospheric expansion, which can cause satellite drag and hazardous to astronauts' life, and the radiation effects in the aviation industry, which is flying across the polar regions and things like, etc. So what are the odds of this happening? So how often we should be prepared, or how should we expect, how often we should expect this happening? So I would like to give that information with the help of introducing solar cycle. Sun has 11-year solar cycle, which is spanning from a period of activity from low to high. So as you can see, this is the trend that is followed by the sun in terms of activity, and we are currently almost here. We are currently in solar cycle 25, and we are approaching solar cycle in the maximum of solar cycle 25. So we should expect some adverse effects, such as very high energy coronal mass ejections in this time, and we were right. So there, I will introduce a few solar events, solar space weather events that happened recently. So in 2022 February, when we are about here, that is when we are starting this in the maximum of solar cycle 25, there happened a thermospheric expansion, and which causes which caused the SpaceX satellites experiencing a drag, and hence the subsequent loss of these 40 SpaceX satellites. So which was in the beginning of solar cycle 25 here. So now we are about to reach the maximum of solar cycle 25 about here, and so as we expected, we got a very major event on January 2022, which is accompanied by X-class solar flare, which is categorized as a very intense solar phenomena. So this event triggered a discussion whether it has something to do with the disrupted mobile communication in one of the major US mobile phone carriers, and it also triggered discussions regarding whether it has something to do with some radio disruptions that happened in Australia, Indonesia, India, and East Africa. So these are some Twitter discussions from some scientists across the world. And fun fact, Sun also had a major coronal mass ejection just a few days before Valentine's Day, and it looked like a big heart from the sun, and it happened in February 10th this year. So there are greater possibility of these events happening. So we should be prepared for this. So since we now know the importance of studying coronal mass ejections, its impacts and things like that, we are a network of PhD students which are part of a PhD network projects which is funded by the European Union called SWATNet, and we have 12 PhD projects which is dedicated from studying the sun, from sun to the earth, and from inner layers of the sun to the earth magnetosphere. So I'm handling project number 2, which is dedicated in understanding the magnetic field intensity which is carried by coronal mass ejections to the interplanetary medium. So our network is named as SWATNet, which is aims to breakthroughs in physical understanding of key agents of space weather at Earth. And as a part of the project, I'm here at ESA Space Solutions IPN, and this is my colleague Slava, and this is Joanna. So we are here together. Joanna will be like helping us in doing our industrial experience here. So moving on. So I am specifically or more particularly studying CME magnetic field prediction, etc. So in order to address that first, we need to understand, to forecast, to understand, and hence to be prepared of these space weather events, or more particularly the CME events. We first have to understand what are the gaps in CME prediction. So the first gaps is we need to know the likelihood of the CME occurrence directed towards a specific location, or in our case, we are more interested in the CME that are directed towards Earth. And the second question, whether this particular CME is going to hit us or it is going to miss us. So that's a binary question which should be addressed with a very specific yes or no question. So we need to address that too. And next one is the impact duration. Even if it is directed towards Earth and it is interacting with the Earth magnetosphere, how long that impact will be affecting us, or what is the impact duration in short. And the next is mass density. Mass density is the amount of mass that is carried by the coronal mass ejections to the interplanetary medium, which help us to calculate the impact, CME impact, or the momentum impact that it can cause in Earth. And the speed of arrival, which is also helping us to calculate the time of arrival, the momentum, the pressure that we will be experiencing in the Earth magnetosphere and the space weather, other space weather impacts, and of course related to the time of arrival, when this will hit us or not. And last but not least, but not very importantly, the magnetic field it carries, and which determines the intensity of the impact. So I am more particularly studying the magnetic field of these coronal mass ejection at its early evolution stage, that is when it started to when it's starting from the near sun environment. So my study is dedicated in understanding magnetic field of the CME in near sun environment. So as we know, we need to study CME. So what is the importance of understanding the near-sun magnetic field estimation of the CME, and what are the challenges? Even though we are particularly interested in understanding the amount of magnetic field that is transferred to the Earth magnetosphere, it is very important to understand the magnetic field of the CME events when it is starting, that is at near-sun environment, because in that early evolution stage is very crucial in understanding its evolution, the travel, the dynamics, the energetics, and hence the geoeffectiveness. And more particularly, when these huge expulsions is happening, the southward interplanetary magnetic field component is very important to understand the how much the impact when it is directed towards Earth. So the southward component of this magnetic ejector is really important. And what is really the limitation of this study? Currently, we don't have a routine observations of near-sun magnetic field estimation. We only have some interrupted radio observations. So we need a methodology to estimate these near-sun magnetic field at its early evolution stage. So this is the motivation or aim of my PhD research. So in this methodology, what we are relying on is the concept of a conservation of magnetic helicity. So I will try to explain what does helicity means. So as you can see, when there is solar eruptions, and when solar eruptions happens, there is some twist, kink, right of magnetic field lines that even can be seen in observations in which is in situ observation and remote sensing observations. So these magnetic helicity is quantifies this twist, shear, and linking of these magnetic field lines, and it quantifies this linking and kinking of the magnetic field lines. So there are studies which estimated the threshold of which, when these threshold of helicity exceeded this, the solar source active region, which is likely to erupt. And there is conservation of magnetic helicity. So when if we are able to calculate the helicity that are available in the source active region, we are able to calculate the helicity carried away by the CMA. So CMA appears as a necessity for the solar corona, which act as a valve to release the excess helicity from the solar atmosphere to the interplanetary space. So we rely on the conservation of magnetic helicity principle to calculate the helicity carried away by the CMA, and hence to calculate and hence relate this helicity to the magnetic field of the CMA. So what I do? First, as I mentioned, this is my first step. I take vector magnetograms of the solar source active region and calculate the helicity budget of the solar source active region before and after eruption. So we monitor this vector magnetograms in a continuous temporal scale and evaluate the difference in helicity before and after eruptions. So we are using a method called connectivity-based metrics method, which is by Jurgulis et al. 2012. So this method helps us to calculate the helicity that are inside the solar source active region. So after calculating the difference in helicity before and after eruptions, we then calculate the geometrical parameters such as radius, length of the ejected CME using GCS model fitting. So this is a representation is how we do that. We do modeling, GCS modeling, and fit a GCS model, a wire-like model in this, and estimate the radius, length, etc. of this CME. And after having this helicity budget estimations of the CME and the geometrical parameters of CME, we relate these two and estimate the magnetic field at the near-sun environment. After estimating this magnetic field at near-sun environment, we often have measurements at near Earth as well. So comparing these two, we do understand how the magnetic field like evolved from near Sun to Earth. So after analyzing, so this is the methodology we are following. So after analyzing events, we are looking forward to create a database of events which is useful for the community to draw understanding of the CMA axial magnetic field as well as the variation of the CMA magnetic field when traveling from near Sun to Earth. And this understanding will help us to give initial conditions of inner heliospheric CMA propagation model. So this is by inner heliospheric propagation model. What I mean is there are models such as which studies the propagation of the CME. So we try to input our results into these models. So one such model is euphoria. This is a representation of how this modeling and propagation works in a heliosphere. So this is the methodology we are following, and by following this methodology, we recently analyzed CME, which has happened in 10th of March 2022, which is observed by the Solar Orbiter spacecraft. So what's so special about this particular event? So what happened is on 10th of March 2022, the CME is observed by the Solar Orbiter like this, and this event is temporarily tracked by the Solar Orbiter and the space by the researchers. So after the observations by remote sensing, it is also observed in situ at 0.43 AU by Solar Orbiter, which is marking a magnetic field. And then after that, around 13th of March, it also observed near Earth. The measurements are also got near Earth by wind spacecraft. And this CME triggered the beautiful aurora in Earth atmosphere. So this is the comprehension of this event. So what we did is in more detail, we tracked the CME into its solar source active region and identified it as it happened at active region named 12962, and this is the active region from where the CME is erupted. So at the time of eruption, this figure represents the spacecraft configuration at the time of eruption. As you can see, the yellow dot represents the sun, the green dot represents the Earth, and this purple one is the Solar Orbiter, which is almost in between the Sun-Earth line, which is at a 0.43 AU. So the Solar Orbiter also got observations of this particular CME. And it also got observations from two other spacecraft named Stereo A and B, which we used for understanding the geometry of the CME. So this is the in situ observation signatures, which is recorded by Solar Orbiter. This measurements is used to estimate the magnetic field that is recorded in Solar Orbiter at 0.43 AU. The upper panel represents the variation of 3 magnetic components, and the black curve represents the magnitude of the magnetic field. And this is the observation by wind spacecraft, which is observed at 1 AU. And here also the first panel represents the magnetic field components, and the later panel represents the plasma parameter variations, which also helped us to record the time at which the CME is recorded. So these two observations help us to understand the maximum magnetic field recorded at 0.43 AU and 1 AU. So to implement our methodology, we first calculated the helicity budget we first raised the helicity budget of the solar source region in a temporal evolution manner, and we marked the CME onset, or the time at which the CME erupted the solar atmosphere. And we in the first panel, you can see that this is the dimming start time, or the time at which the CME started to erupt, and this is the dimming peak time. So there is a difference in helicity that is observed before and after eruption. So this difference in helicity is assumed to be bodily transported to the CME. So these two are the variations of the intensity variations that is observed in the images, which has helped us to identify the start and end timings of the CME. So we estimated the difference in helicity that has happened before and after eruption, and we noted the value. And after that, we used the multi-viewpoint observations from LASCO and Stereo to fit our GCS model to understand the radius and length of the CME. So after getting that, we relate this this helicity budget, which is represented as H, the radius length of the CME, to the magnetic field of the CME, and hence we estimated the magnetic field which is associated with the CME in the near sun environment. So After estimating the magnetic field of the CME at the near sun environment, which is a height which is obtained from the GCS model fitting, we use a power law index variation, power law variation of magnetic field from near sun to Earth. So assuming power law variation, we fitted a linear fitted this magnetic field measurement from near sun to Earth, and we also have a in situ observations at 0.43 AU, and we got a power law value of 1.29 plus or minus 0.18 for this variation of the magnetic field. So after getting these results, we use these results of as input to in a heliospheric model such as Euphoria. So in a conclusion, we estimated the magnetic field, the near-sun magnetic field of the CME as 2067 plus or minus 405 nanotesla at 7.6 solar radius, and we estimated the power law variation of magnetic field of the CME as minus 1.3 plus or minus 0.8 value. So these are the major results of our study, and we are looking forward to give that to the inner heliospheric models for better understand and compare our methodology and better understand the power law variation of the magnetic field. So here at IPN, I'm planning to visit a few startups which are designed which are dedicated in terms of space and space weather effects. So we will be visiting the startup Spotlight Data, Geosat, and Materio for more potential collaborations and future discussions of our technology or the ideas that we are having. So yeah, thank you. Thank you for listening.
Thank you so much, Shifana. I have here one question. So clearly, studying the CMEs, it's very important, mainly even for satellite health. And so, do you think, do you believe, or do you think there would be a strategy to not only just studying, but do you think that it could be interesting to create kind of a strategy, a platform, something that could help us measuring the health of satellites? Are I mean, is the health of satellites really registered, or because I mean, with the CMEs, they can stop working, or there could be some telecommunication problems. So, do you think that would be, I don't know, any strategy, any kind of different application?
Yeah, there is a necessity of monitoring satellite health. So yeah, which also includes to reduce the space debris problem, and yeah, I think the importance of yeah, I do agree with the importance of the necessity of monitoring satellite health. And in space weather context, it's also important whether if like in collaboration with what I was doing, if we are able to monitor these space weather events in advance, we can make a protection to these satellites at the duration of impact, and then again turn back on for normal functioning. So yeah.
Yeah, that would be an interesting topic to not only to measure, but also to not only to measure the satellite's health, but also to see if we could kind of find a platform or something that could measure the health of satellites. It could be specifically with CMEs, but it could also be specific with other kind of radiations.
Of course, yeah. Yeah.
Yeah. Okay. Well, I think that this is a very important topic, and there could be different applications from this. I don't have any other questions. I don't know if anyone who's listening has any other questions. If not, I think I can. I'm going to stop recording. And well,